This is Richard Walker from Lucidate. Welcome to the 7th video in this series where we look at applications of AI to computer vision. We've looked at a popular type of AI called neural networks, modelled on how our brains work. Simple processing units called neurons comprise individual layers. These layers are stacked to form a network. We've seen that by training these networks on labelled training data, they can learn to classify images. They do this by nudging weights that connect neurons and biases inside neurons. The result is a crazily complicated multidimensional function, a function that can very accurately classify images that it has not seen. We've also looked at how we can combine these networks as ensembles. Here, diversity improves accuracy. In this video, we're going to make these networks break. We're going to show that under more demanding scenarios, they aren't that accurate at all. We're going to show this to motivate a new architecture. This new type of neural network is much more robust for image classification. Networks with this new architecture are called convolutional neural networks, or CNNs. Furthermore, this architecture shows great promise for other areas outside of machine vision. In past videos, we've seen accuracy scores of well above 90% for our clothing classification task and over 98% for digit classification. Given this level of accuracy, you might be surprised to hear about the need for new architectures. But the reality is we've been dealing with very easy examples. For both the digits and the clothes examples, the images are simple. They're monochrome, they all have plain backgrounds, and the orientation of the images is consistent. If we introduce colour images with noisy backgrounds, the task gets much harder. It gets harder still if the subject can be in any orientation, rotation, or perspective. Here is such a dataset. It contains 10 types of subject. 4 are vehicles, planes, cars, ships, and trucks. 6 are animals, birds, deer, frogs, horses, and of course, cats and dogs. As you can see, they're colour images. They have variable poses and perspectives, as well as noisy backgrounds. This is a far more realistic challenge than the contrived examples we have looked at to date. Let's use the same configurations of neural networks as we had in our previous Olympic Games of neural nets for our digits and clothing examples. We'll change the input layer to take into account that these new images are 32 by 32 pixels with 3 channels, one for red, one for blue, and one for green. The hidden layers and the output layer will remain the same. We can see here that on this new dataset, the network's performance is poor. This is the 7-layer network that won this particular competition, but as you can see from this analysis page, we're not seeing accuracy scores in the high 90s. Here we see 48 images of cats that were incorrectly labelled as cars. The accuracy of our gold medal winner is less than 39%. Most of the networks in this batch didn't achieve anything like that score. The majority fared little better than 10%, which is the same as random guessing. If we take an ensemble of our best 4 networks, we can increase the accuracy score to over 41%. Remarkable and credible, but not high enough for any practical real-world classification task. So let's take a step back here and see if our intuition can point us in the direction of a better architecture. The architecture we've been using so far goes by the formal name of the multi-layer perceptron, or MLP. Here we connect every neuron from one layer to every neuron in the next layer of the network. Our input layer, which, if you recall, is the pixel intensities of our 2D image flattened into a 1D vector, is fully connected to the first hidden layer. Each hidden layer is fully connected to the next. The final hidden layer is fully connected to our output layer. For image classification, Indeed, for many other tasks, this might appear wasteful. Our intuition might tell us that for any given pixel or any given piece of data, the information that matters most is the immediately surrounding pixels or immediately preceding or succeeding data. The intensity of the upper left pixel relative to the intensity of the lower right pixel might have some limited information content that helps us classify a particular image, but the chances are that it doesn't. But the relative intensities of neighbouring pixels, left, right, up, down and diagonally, will have much more information content to aid classification. We can learn from biology. In their 1981 Nobel Prize Award for Medicine, David Hubel and Torsten Wiesel showed how cells in the primary visual cortex were strongly activated by lines of a given orientation. In other words, edges. Where these edges intersect, we have corners. These edges and corners can be built up into primitive shapes and then into more complex patterns that we can classify as objects. Might we be able to combine our intuition that the relative intensities of neighbouring pixels matter with the work of Hubel and Wiesel on edges and orientation? This is the motivation behind convolutional neural networks. The convolution operation involves creating small two-dimensional filters and applying these filters to our image. These filters can be of any size. For our examples in this video, we'll stick with filters of size 3 by 3 pixels, but larger filters are very common. These filters are applied to our image to pull out features like edges and corners. To see how they do this, let's work slowly through a practical example. Here's a small fragment of an image, highly magnified, with the pixel intensity shown as numbers and as shades of grey. It's a 7 by 14 fragment of an ankle boot, with this fragment showing the area around the sole of the boot. In yellow, to the left of this image fragment, we see a filter. We've arbitrarily assigned weights to this filter, -1, -2 and -1 in the top row, 0, 0 and 0 in the middle row, and 1, 2 and 1 in the bottom row. The reason for this assignment will become clear. Let's apply our filter to the pixels in the top left corner of this image fragment. We'll multiply the weights in the filter by the pixel intensity. We'll sum up these 9 products and take an average. The average here is 5. We'll then create an output image and insert this pixel intensity in the top left pixel of this new image. We then shift our filter 1 pixel to the right and repeat the operation. Multiply the weights in the filter by the pixel intensity. Take the average of these 9 products and insert the value into the output image. Here, the value is -15. We will typically use a ReLU and record this as 0, not -15. But I'll keep the sign in for now so that you can follow along with the maths. I'll show you why we can drop the sign in a couple of minutes. This process continues until we reach the right edge of the image. Please feel free to slow down the video if you want to check the arithmetic yourself. Always a useful exercise. Once we've reached the right side of the image, we drop our filter down 1 row and return to the first column. We continue to repeat this convolution operation until we've run out of pixels. What we have here is a horizontal edge detector. The top part of this image fragment is the boot. The bottom part is the background. As the filter passes over the boot, all the pixels are close in intensity. The orientation of the filter with the negative numbers in the top row and positive numbers in the bottom row mean that the convolution operation produces a value very close to 0. And this also happens when the filter encounters the white background at the very bottom of the image. The pixel intensities here are all close to 255, which is white. But at the boundary between the sole of the boot and the background, the filter becomes highly activated. It produces numbers a long way from 0. This is part of the reason for using the ReLU. the polarity of the edge from light to dark or dark to light might have information content for classification. So this filter is oriented to find horizontal lines. Let's zoom out and look at our full image of the ankle boot. There's the area around the sole that we've seen. We also have an arch characterized by a diagonal line from lower left to upper right, as well as the heel, which has two vertical edges and a horizontal base. If we apply the filter that we've used on the sole to the heel, we can see that it picks up the base of the heel as an edge, but the orientation of this filter does not pick out the two vertical edges. But if we rotate this filter so the first column contains -1, -2 and -1, the middle column contains 0, 0 and 0, and the final column contains +1, +2 and +1, then we can see that this filter does indeed pick up the vertical edges of the heel. We can build diagonal filters too. The horizontal filter picks up an edge of the arch, but there's a much stronger activation from our diagonal filter in this particular part of the image. Filters are activated by edges, but also by textures. Textures are changes in pixel intensity. Think of the difference between a thatched roof or a smooth steel building, or a tarmac road and a tree. One can deploy larger filters than 3x3 to look for textures in an image. When I was researching for my PhD back in the 1990s, we thought it was a good idea to code these filters ourselves, hard coding the values like -1, 0 and 1. This would explicitly look for certain edge orientations or texture types. This turns out to be a terrible idea. We've learned a lot since the 1990s. Better to let the backpropagation algorithm determine the right filter weights based on the training data. So let's return to our first example and remove the sign just to look at the absolute values of the resulting pixels. Once we've run the convolution filter over the image, it's common to run a further filter on the resulting intensities. This is called a max pooling operation. Following a 3x3 convolution operation, we typically use a 2x2 max pooling filter. This takes the maximum value from the 2x2 region of the resulting image. This will downscale the image and extracts the maximum activation from the filters applied to that image. Once we've found the edges and downscaled, we'll run the convolution and max pooling again. The first pass will extract edges. Successive convolutions and downscaling connect these edges into lines and corners. An intuition for this process is transforming the image from its raw pixel intensities into a map that contains edges, corners, and primitive shapes. The results of this feature map can then be fed into the multi-layer perceptron architecture that we used before. You can see from these results that the feature extraction provided by the CNN has a huge impact on the accuracy of this classification task. We see an accuracy of over 74%, and in this case, only 2 cats have been labelled as cars. This level of accuracy is getting close to a level that might be useful in practice. If we combine our top performing networks into an ensemble, we can push the accuracy up to over 81%. There's quite a spread in the accuracy from the worst to the best, and quite a pickup from the best single network to the accuracy of the ensemble. The best performing CNNs on this CIFAR-10 dataset have shown accuracy of over 94%. I hope the intuition here makes good sense. Rather than feeding in raw pixel values into a perceptron, we're performing some pre-processing to extract the salient features and patterns from an image. This CNN approach is at the heart of biometric classification for facial and fingerprint analysis. It's also used for number plate matching and of course driverless cars use this technique. Each layer of our CNN network will have several filters, each filter tuned to extract specific orientations of edges or textures. In our first layer, it would be common to have 32 different filters, maybe more. As we run these filters on an image, we generate multiple processed copies. When we apply max pooling, we'll reduce the resolution. Each of these copies will then be passed to the next CNN layer, and each copy will have multiple filters applied to it. This will lead quickly to an exponential increase in the number of copies of images processed by the filters at each layer. Here I've shown an example of 4 filters applied to an original image of a bag. I've shown 4 filters so that they can fit on the screen, but bear in mind we would usually have many more than this. If we have 32 filters in our first layer and 32 filters in our second convolutional layer, which is frankly common, then we'll have 1024 input images to be processed by our third layer. The max pooling operation will reduce the computational load. Remember, max pooling will reduce the size of each processed image, but the amount of data handled by deep layers of CNNs can get extremely large. In this video, we've looked at a new architecture of neural networks, convolutional neural networks. These are inspired by our understanding of the human vision system. They extract features by applying very localized filters that are activated by large changes in neighboring pixel intensities. Through a repeated application of convolution and downscaling, edges, lines, corners, patterns, and textures can be determined. Feeding these pattern activations into a multi-layer perceptron yields better results than raw pixels alone. This is Richard Walker at Lucidate. Please join me in the next video where we will look inside these CNNs to visualize the filters and patterns that they form. We'll also apply these CNNs to our original digits and clothing classification task to see how much improvement we can gain by using this technique.